which is more in type of a topological picture. So let's draw the surface. So here you see a surface. And we have a notion of genus. So I draw for you what I call broken glasses. Broken glasses. So take off your glasses, remove those things, and put it on a chair and go and sit on your glasses. Then you have broken glasses. But topologically this means you have the following thing. I draw for you a broken glass here. This is one, and this is the other. And what you see here, they are not like this. They are like this. One goes on, and then the other goes behind the blackboard. So they look like this. And this I call a pair of broken glasses. These are two curves, two simple closed curves, which intersect in one point, and at the intersection they are transverse. One goes to the other side corresponding to the other. So they cross like the x and y axis in the plane. And such a thing is called a pair of broken glasses.
Can you get the darker pen again? That's almost invisible. Is there a darker pen?
Yes.
That's almost invisible.
What I do is this one.
Huh? Isn't there a better one?
On the table?
Here. Here is better.
Merci.
Yeah. So, genus. Genus is the maximum number of broken glasses on the surface. So here I can draw for you another such broken glass. So here, another one. So here we have two. To make this visible again, so the maximum number of disjointly placed broken glasses on the surface, that's the genus. So that's a practical way of quickly see the genus. First, you try to put the first one, and then you simplify the surface in the following way. You walk around the broken glasses. That is a long walk. And then go back. And what you do, you take your scissors and cut it along this. This takes away from the surface something which looks like this. This takes away this. The dotted curve is the walker curve, and then this takes away this. And now, if you took away, you fill this by a disk, and your surface simplifies. And then in the remaining piece, you try to put broken glasses. If you can do this, okay, you do it, and remove by walking around, and you proceed this way, and the surface simplifies, till you cannot put any more broken glasses. So, on the two-sphere, you cannot put broken glasses. If you put the first curve, and you must be transverse, then you must join those two ends. But they are on different connecting components. So there's no way of joining. They call broken glasses or two simple closed curves which meet in exactly one point. It's not allowed to meet in a second point. So this gives a quick way of seeing the genus. This is the same as what we had yesterday, a quick way of seeing the genus. So for later on purposes, so the surface is oriented. So now I choose an orientation on the surface. So an orientation on the surface go to the shop, buy a watch, and look at your watch, and you see the orientation. It seems that all watches in our world turn the same way. In some way, this is a proof that our world is oriented. So, that's an orientation. If you have an orientation on the surface, this has a lot of consequences of other orientations. For instance, when I have an orientation and I have two vectors which cross, I can assign to them plus or minus 1. So to this, what I do, I take the vector which one arrow, then work according to the orientation. I orient the record also by the same watch. And then hit the second. It could be that they hit the second in the direction it goes, but it could also happen that when I do this, the second vector, so I walk like this, and then I see I hit the second vector at the other end. In this case, I say plus 1, and in this case, I say minus 1. So when two oriented curves intersect, I can attach a number, plus or minus 1. So what I do here is I orient the curves in such a way that at the intersection point, the side is plus 1. So I do this. And then I give names to the curves. The first curve which I oriented, I call A, and the second I call B. And here it is genus 2. So for the first broken glosses, they're called A1 and B1. And for the second, I do the same. One is called A2, and the other is called B2. And if the genus is 3, we have A3, B3, and so on. So we get from the notion of genus, and by realizing the genus, by putting broken glasses on the surface, we get a system of curves which has 2 G elements. On the curve, we have altogether, we have 2 G curves. And the curves are labeled A1 to AG and B1 to BG. This will be of use in the next time. But we wish to understand the space. So we should slightly forget surfaces for a moment. So just take a second and forget surfaces. Forget is very difficult actually. So please forget little surfaces. So we have a space, the topological space. And I take again the favorite example, the space Y. You know space Y is exactly I mean what is drawn here. And then we have space X. And I wish to study this space by measurement. So historically, people tried to measure the Earth. They had a huge amount of funding needed. They sent ships away and they measured about the Earth. And this took a lot of amount of resources. And then they had many informations about our Earth, which you can say functions. So there was one ship going away and was measuring the temperature at every point of the Earth. Another ship was measuring something else, humidity and so on and so on. You have many functions you measure along the Earth. Each function was extremely expensive, so you got a few amount of function because the funding was limited. But then came mathematicians. The mathematician says function is for free. We take them all for free. So we take the space of all functions on our space. So all functions on our space. All functions, all continuous functions on the space. The space here is this letter Y. So what we can do in this space? If you have two functions, you can add them and you can multiply them. So altogether this means it makes a ring. So each function is a measurement and we do all possible measurements, but we information is carried by the ring. Question? It's slightly simple question is all the rings C0 by this ring and the other one isomorphic. Is inside the ring enough information to say that this space is different from this space? Somebody knows the answer? So you are extremely rich. You have so much funding that you can do every measurement you like.
So the ring of all continuous functions is rich enough to restore the topology. I say it with those words, if I make this leg longer, which refers to the fact that we would have a metric. If I do not have a metric, if I have a topology, I cannot say how long are those legs. But if I have a metric, then I can say how long they are. Here I say stores as information to topology and not the metric. You do not know about the shape. If this y is in the plane like this, do not see. And which one is longer, you do not see. But the space stores, the ring stores the topology. You know this theorem? You should know, because that is the only reason why you have, if you study physics or mathematics, you study functions. It's the only reason. If there would not be such a theorem, this notion of function would disappear from your curriculum. No need for functions. Proof is rather simple. I try to give this badge later. So, before getting the proof, let's first give a hint. What would be, in the terms of ring, a point of the space S? Imagine somebody is only interested not to know the whole space, he wishes to know one point. Space is many points and topology. So, let's take very easy spaces. Space of 2 points and space of 3 points. So this is space 1 and this is space 2. All the rings are different. Right? The theorem says yes, because the topological spaces are different. How can we see 1 point? This is something which is very common in practical life. So here we have a ring. And then we go to what we learned at school. At school we have things where we can add, multiply, and we have many properties. The many properties is every element which is non-zero, you can divide by. So, and we have division. And division, I write it like this, means you can divide by elements which are non-zero. And such a thing is called a field. Later on we will have also fields with other nation. And what if you have something complicated, what like our society to do? And a good example is universities. Universities would like to make ranking, Shanghai ranking. So what you like to do is you like to have a map to a field. So a point in S is the same as a map to a field.
Is that a key idea?
Huh?
Is that a key idea?
Is that a key idea?
R is ring, C0 is a ring, but S is not ring. It's not
No,
S is just a set of morphism.
No, I disagree. No. This is a ring.
Yes, but
Ring.
yes.
But S itself
S is
space.
No, it is just a set of morphism, ring morphism.
Yeah, from this ring to this field.
Yes, exactly this. Yes.
You said S was a ring.
No, I never said this.
Ah, then I hear
I said that S is set of morphism, ring morphism. S is set of
ring morphism to a field.
Yes, that is the idea.
Yeah. And it is set of surjective. You get the whole thing. And in our example, the only possible field which can appear here is the field of real numbers.
Yes.
And how is this met? If you have a function, you must attach to this a number. And imagine we have already 1 point. We knew already 1 point in our space. Then the number which you add is the value of your function at functions at a point give you maps from this ring to that field. And the amazing thing is, all points, all such maps correspond exactly to a point. So the maps to fields, to things where we compute better than in a ring, is the same as a space. What I did not tell is what is the topology, how it is hidden inside. And this I do not tell because we do not have so much time. And this is the theorem of Gelfand. Gelfand. So functions are useful. This is so the question we talked about earlier like this. So let's take a graph. So let x and y be finite graphs. So x and y, this is a graph, but no more general. X is any graph. So x could be something like this, and y could be something like this. Then we know already that the rings are not isomorphic. The rings are not isomorphic because clearly they are not homeomorphic. The rings. But what I can do is I can give another meaning to this thing. I remember the addition, forget the multiplication, so there's no more a ring. But I remember the norm. This has a nice norm. The norm of a function indicates x is compact. The norm of a function is the supremum of this function where p runs over space x. So when this symbol here is together the notion of addition, I forgot to say, we also remember multiplication by scalars. So when we have a function and a number, we can talk about lambda times that function. So this is a vector space. With norm. So that's the information which we have. The question is, how much information is stored inside this? Can you reconstruct the topology? Here we are more algebraically thinking. We stress the two operations, addition and multiplication. Here we are more functional analysis thinking. The keyword for this space is a Barnum space. The question is, how much information is stored in the Barnum space?
You have also dual.
You get completely other panoply of possibilities.
No, because you have norm, you have
I think complete other world of things you can do, of mathematical operations. You put one example and two of them. So the answer is, and this answer the Banach spaces the Banach at least one edge is, well, the graph has at least one edge. Or isomorphic. Isomorphic. Not if and only if the Euler characteristic of x equals the Euler characteristic of y. Euler characteristic of a graph is the number of vertices minus the number of edges. That's the theory. It is in the notes. Question. This is something young people can do on the way home, but I cannot do it. Question. Is this if, in fact, if and only if? Is this thing also if and only if? That would mean, can the Banach space of functions see the Euler characteristic? Is the Euler characteristic stored inside the Banach space of functions? To prove of this is in the notes, not extremely easy, but also not extremely difficult. Something recent in the middle. And of course, this question goes also for surfaces. So, if you now take the Banach space, I write like this. When I write this, that means a vector space is obvious, and we have only the norm. And does this thing see the genus of the surface? In this line, S is the surface. I do not know. In the case of graphs, I do not know if it sees the Euler characteristic. You can also say, does the Banach space of continuous functions see the Euler characteristic? Yesterday I have seen Euler characteristic in genus already.
Why don't we also consider diagonalization of forms in the Random homology, for example?
It's continuous functions. If we take, and that is next, if we take differentiable functions, then we see the genus.
Yes. We shrink the class, but we extend the grade first.
Yeah. So we are on the level of continuous functions, and then we have the Banach space of continuous functions. But if you wish to do the round homology, you said, you need a little notion of derivation. It's little d somewhere. So better your functions or differentiable functions. As soon as you have your differentiable functions, you can do more. But on the level of continuous functions, you cannot do this. So, now we wish to study more functions. We go to functions. We should, instead of studying continuous functions, we immediately start studying differential functions. And we do something very modest. We have U, the subset of V. V is a vector space, a real vector space. Real vector space, finite dimension, and U is open subset. So we study functions, we have an open subset inside the vector space. I apologize, I tried my lecture in the cafe yesterday doing all four here, because I need to know, so you claim not to know everything. So by extrapolation, I think all the others also don't know everything. But this is perhaps completely wrong. But you are the co-wise. Thank you for doing this yesterday. So we wish to study functions defined on U and functions with real values. And we wish to study differential functions. So I do for scratch what I'd like to know first. So when we have a point P in U, I wish that we understand the differential of f at the point P. And first thing I say, this differential, then the differential of f at P is something. Something it is a map from ambient space, ambient vector space, to the real numbers. Then this at P is this thing, a linear map. So the differential is a linear map. I did not tell which one is a linear map. It's a linear map that fits in a three-term expansion. So this linear map, the main use of this linear map is to get insight concerning your function, which is of local nature, concentrated at the point P. So this gives us local information of the function at the point P. It's three-term. So I said open set. Here we have U. Here we have P. What we can do is we can draw some ball around that point P. Local information is that I tell you something about the function if I look only, if I restrict my function to that small ball around me. So we start taking points in that small ball. So this P plus a vector. So this P is a point, and this H is a vector. And we have the three-term expansion. So we have term 1 plus term 2 plus term 3. And the terms, I do not give immediate formula, but I characterize them by properties. The property of this term, it is independent or does not depend upon H. So this term, if I vary H, this term keeps the same value. The second term is characterized by a property. It depends on H, but in a very good way. Depends in a linear way upon H. And this term is characterized by a property which is stored in notion of size. So this was the vector space of finite dimension. So on this vector space I can take a norm. There are many possibilities, but value of b plus h. This is a function of b plus h. And this is a function of b plus h. It is a function of b plus h, but I wrote does not depend on h. And here, it does not so depend on this b, but depends on h. And here, I write something different. So, what I write is that I wish to be short. I take the limit for h goes to 0. So this is a number. So I take absolute value divided by the size of h, the norm of h. And I wish that this limit is 0.
This is in the first page of the paper.
Which paper?
The one you put, I don't know where I got it, you sent it to me.
Yes.
That's in the first page.
It's in the first page.
Now, I just want to know how everything fits together. Because we are in 1.5 days of your talks.
No. We did the talk before. I started in the middle of the page.
Okay, so I just want
if this is the lecture, we started here and we run like this. We do not do this. So don't be afraid about how it fits.
Well, I just want to know how to study your paper. Okay? Whether I can start from different points or whether and pick what I want or whether.
It's a random walk.
Hmm?
It's a random walk.
This
Okay,
depends more. This depends more upon you as on the paper.
Yes! This is why.
I am not qualified. I'm not qualified.
Because, sorry, I have a great respect for you. Okay?
And vice versa.
And I am the one who invited you. Okay? But my point is, first and foremost, for me, it is me.
Yeah.
My wife.
No. We had this morning in the cafe a discussion, and in old days, some people were thinking the Earth is the center of the universe. And then we came to the conclusion, each one of us is the center of the universe.
Okay. Why I'm asking that? Because you started at such a fundamental level that now, when you invoke a limit, then we say, okay, what are the concepts, okay, that is there some concept more primitive than limit that goes into the concept of limit?
Yes,
so
yes,
is
yes,
that
yes,
concept in your lecture?
Yes, I answer yes, and then I say, we do not have time to go inside this.
Okay, good enough. So I don't have time in my life to connect.
No, sorry.
What I'm doing.
There's a question.
Yeah.
So, can I use this pause just to get back to the graphs? About the question, if and only if. Is it about the graphs being critical?
Of the graphs?
The graphs are critical. You cannot remove an edge without breaking the watching.
No, for me a graph is a collection of points, which are called vertices, a collection of edges, and they are attached to each other. And they are attached only in the endpoints. So this point on its own is already a graph. But here I say it has at least one edge. Then an edge is already a graph. And if we have to have more graphs, I can attach to the endpoint a few edges. And I can continue. I can add here a few. And then I can add here one. So a graph is a collection of finitely many intervals, 0, 1 intervals, attached at the endpoints. That's a graph. That's a finite compact graph. And then this question and statement concerns only compact finite graphs. And then the last line, this is a surface. The surface which we studied yesterday, compact, oriented, and I forgot what. a function is differentiable if at every point B we have a such three-term expansion. When we have at every point such a three-term expansion, we get a new creature. That is a function from U to a space which is much more complicated. This is to the dual space of the vector space. I tell you what is the function. To B, we attach by this map the differential of f at the point B. That is an element B. Because we have seen here, the differential was a map, linear map, from B to the R. And the dual space is nothing else than the collection of all such linear maps. And a function is twice differentiable if we can differentiate this thing. So we can compute the differential of this map at point B.
Why did you put capital D and not another?
Because I put it here.
Oh.
I put it here. Here I put it on purpose. And here I define the map. Every point I attach this gadget. This map I give a name. The name is written here.
Yeah.
Small df. So it is the thing is attached to a point, a linear map. So this thing will be a slight generalization of this story. Small df is a map from V, from U to V star. So the differential of this is a map from V to V star. And is characterized by an expansion. Is characterized by an expansion where these four terms fits in f of p plus h equal to. No, we start thinking when this term does not depend on h. And those terms are zero when h is zero. And a linear map evaluated at zero is zero. And this thing, if this limit is zero, then better this thing is zero when h is zero. So now I can start computing this. This is nothing else as the value of our function at the point P. This term I can compute. This is nothing else as the differential of f at the point P plugged in the vector h. And this is the term we neglect. So here, I know already in the beginning. And then comes first term. And you told me I should speed up. So I immediately use the notation. I write in the series above. Hashing of f at the point B, evaluate, Hashing is a quadratic form, evaluate it, you can plug in the vector twice, and then we have term 4. And term 4 is small in this sense, but we also have a square here. Term 4 satisfies limit for h goes to 0 of term 4 h divided by norm h squared is 0. So people say this higher order. So we have this hash. So this is not 0 in general. Now the question is, imagine we know something about the differential. Can we say something about the function? I told you differential is needed to say something, to have local information about the function. That's all. So, F goes from U to the reals. U is like before, an open circle in the vector space and so on. And we have a point B in U, so I have this B ready here. And we know something about this differential. So this differential is a linear map in some vector space, which I do not know. What can we say about a vector in a vector space which we do not know? What we can say? We have a vector space, we know nothing about it. And I wish to say something about one vector.
How big it is?
No, cannot say. Because then you need to know.
You want addition. Okay, I didn't understand your question.
We have this vector space, we only know it is a vector space. What can we say?
From the differential.
Huh?
Only from the differential.
Oh, yeah. This creature is an element in this vector space. We forgot from where it came. I wish to talk about this element. Which are the sentences which we can pronounce?
Linearity?
Huh?
Linearity?
It was linear, because it is element in this, it is already linear.
See when it vanishes.
Ah, yes. We can say two things. It could be that this guy is zero. You know, the good picture of a vector space is this. A vector space looks like this, like both things we can put on that base. And one element which plays a special role is the origin. So you can say you are equal to this element or you're not equal to this element. So this is an assumption. If we have this assumption, can we then say something about the function? Say something very strong about the function. Of course you can say, yes, it's differential at that point to zero. I also can we say something more. And then we work with this assumption. Can we say something more?
What happens around it?
Huh?
What happens around it? Whether around it?
Yeah. Can we say something more? I tell you what we can say under this assumption.
We mentioned the K.
Under this assumption, we can say the following, that exists. A local coordinate system.
Local coordinate system.
Not talking. Not talking.
Which, what local coordinate system, which I will say what is a coordinate. People say a coordinate, they use this letter. They say first coordinate. But what is in fact a coordinate? It's a map. So a coordinate is the map. We'll do local, so we work in a small ball around our point. So it's a map defined, it's a map to the real numbers. And we have several of those maps, as many as the dimension of your vector space. The quality of those maps is that if you know the values of those maps, you know where you are in your ball. It's a coordinate system. So there exists a coordinate system, x1, x, z, maps on local ball of radius or to the reals, such that now I also want you to write here.
Now,
This coordinate system, you can choose it such that what you write here is extremely strong. So if you can write little here, then this coordinate system is not adapted to the function. If you can write here something extremely strong, then the coordinate system is adapted to the function. I write it for you. F equals first coordinate. sum of the coordinates. It's just the first coordinate. You know this here? What's the name of this theory?
Somewhere in the beginning of motion and
No. It's just before.
yeah, it's in the beginning, but I don't know.
It's a function theory.
Ah,
It's a function theory. It is a function theory says if the differential at the point is non-zero, then by good coordinates, the function is just the first coordinate.
Just change it. You don't need coordinate. You don't need coordinate. F is coordinate.
F itself is a coordinate.
You don't need coordinate.
You don't need. I could make this shorter if I say F is part of a coordinate system. Then I do not need this notation.
Differential is no zero and F is coordinate.
Yes. That's a very strong. That tells you if somebody starts solving equations, for instance, if I wish to know the level of F, so assume 1 over F of B is 0. And I'm interested to know the set of all points where F is 0. So we are on the plane. So I can immediately say the level cannot look like this. Because a linear map cannot have a level which looks topologically like this. So this gives a lot of constraints about the level set. So next theorem is, we did this and I stressed the importance of differential. If the differential is non-zero, I can say a lot. Now we go to this case. Unfortunately, I can say nothing. So if I want to say more, I have to add hypothesis. So what we add as hypothesis, I wish to talk about this, and moreover, we have an hypothesis. Moreover, this creature which appeared there somewhere. So, moreover, I assume something about this creature. And I assume that it is non-zero in a very strong sense. I assume that this map is surjective. If you choose the basis here, and you get it for free the basis there, then this linear map has a matrix, and I could say the determinant of this matrix is non-zero. But I prefer to say this map is surjective. It's irrelevant. And make this extra assertion. Here I want to surjective. So we have differential 0, and this map is surjective. Now I wish to say something about the function, exactly what we hear. So the starting, I do not spell out, the statement is, then there exists a local coordinate system such that the map equals something. So, in now, again, the amazing thing is, somebody who knows only the numbers plus and minus 1. So, imagine you went to graduate school, and the only thing you remember is plus 1 and minus 1. The rest you forgot. And also, by accident, you know what the coordinates is. So, what can we say about f? Yes, it is a constant, it's f of p. F of p. If I put f of p equal to 0, I can forget, of course. Plus minus first coordinate squared, plus minus second coordinate squared, and so on.
We are starting to approach the limit of your talk. So at some point we will decide.
We are already over, or
Well, we are a little bit flexible in this place. But
so study functions. And one of the favorite things is to make, for in French, it is tableau de variation. In French means to tell a function where there's maximum, what it does. So you wish to have a description of the function, so these are functions on an interval, AB. And then a good description is you have maxima, minima. And to make such a picture is called a tableau de variation. And then you have maxima, minima. And then there are functions for which this is not possible. So when I take, for instance, the function x to the power 10, sine of 1 over x. This function, so near 0, it does something terrible. And no way to make a tableau de variation such that you can put on one piece of paper everything that happens. So if you can put it on a piece of paper better, you only find that you manage such points. So the amazing thing is that for every function, if it is 2 times differential, and if you do the following, instead of taking the x-axis, near the y-axis, you take a new x-axis, x prime. The old graph in this new plane is graph of a function. And the function, what you did is you added to the function, better here, this picture, to subtract the linear function. This new axis is the graph of a linear function. And the theorem is that there exist many linear functions such that this function has a tableau de variation, has only finitely many maxima minima, and all those maxima minima are non-degenerate. The second derivative is non-zero. If you do this one dimension higher, you get a statement about the surface. Every surface is the union of d pieces and 2's. Thank you very much.
Where you were talking about, I want to ask if maybe this topic is related to break theory.
I must tell you that this, for somebody who only knows finitely many numbers, this is the end of the story. There are no theorems concerning functions, local behavior functions, where you get a statement such that in the end statement appear only finitely many numbers. This is only true under this hypothesis. Differential 0 and this hashing non-degenerate or differential non-zero. In all other situations, you do not have such a statement. All functions, they have a local behavior which is much more delicate to describe. So these are the 2 basic theorems, and it is it's good for humanity that there are many functions where at the points where the differential is 0, the hash is non-degenerate, many such functions exist. Here this statement says in dimension 1, adding a linear function is enough to promote your function in the realm of those 2 theorems. Those 2 theorems become applicable. So there are many functions doing this. And this is something which is basic. It's called Morse theory. It's a huge generalization and infinite story behind this, but the basics is that you can reduce to an expression involving only finitely many numbers and a well-shown 2 coordinates.
But is this related to break theory in some way? Maybe I translated teoría. No, teoría de grado. Break theory. Maybe when you have a function and you want to know a function f is equal to a number.
Yeah. That gives the level set of this function. Okay. You wish to study the level set. If you have this hypothesis, then the level set looks locally like the level set of a linear function, which is an open set in the linear space. And that means, in fancy words, the level set is a manifold. If you have this hypothesis, then the level set is except in a few other points, if your manifold level is compacted of only finite many points, the level set is a manifold, and where the level set is not a manifold, something you can describe in terms of those plus minuses, and for surfaces this is very easy, something you can describe happens. So you have a complete control about what happens. And typically what happens, if you have such a piece of surface, our t piece, and the function is the height function, then here we have a point where the differential is 0. And what happens at this point? If I look above, I have two circles. If I look below, I have one circle. So the action is, if you go from below to above, two circles merge. If you look the other way, so if you have two circles, they can come close together and they make one circle. But this one circle looks like this. And you have the opposite procedure. If you have one circle, you can pinch in the middle, you have two circles. So this theorem, this is the only thing that happen. And if you know this, then it is almost clear that you can decompose your surface in t pieces and cubes and caps. Because the other picture is at the maximum, it looks like this. At the minimum, it looks like this. And then at its center, it looks like this. This is a proof. But what we need to know is, we need to know that also for functions of two variables, a slight perturbation changes your function into a Morse function. That is Sartre theorem. Sartre theorem. Achtung, Sartre theorem. This is surjective maximum rank. Surjective maximum rank. Because also because the V and V star and finite dimension of the same element. In functional analysis, I should say more.
Okay, more questions?
Yeah.
Are there more questions? Okay, please. Okay, let's make this quick.